Hello, what you are watching right now is an animated QR code. The standard QR codes have a maximum data capacity of around 3 kilobytes, and they look like this. In practice, these dense QR codes become unreadable if you have a small screen or bad lighting conditions. So, the solution is animating them. And how are we moving this much data reliably? I'm İrfan Bilaloğlu, and I maintain BCUR JavaScript library that powers this. And today I'm showing you how to create and read animated QR codes and why they are becoming the standard for air-gapped hardware wallet communication. The magic of the animated QR code is that it's just not sequential data. It's using fountain codes. What this means is, here I can show you on the screen, is it goes sequentially up until a certain point. And from this point, the magic happens on the next frame. You see, this is the part 7 of the 9 generated QR codes. And this has data from the first block, second block, and fifth block. What this means is, when I'm reading all of these QR codes, if I somehow miss the third one, or my camera wasn't just fast enough, or lighting conditions were bad, I can reconstruct the original data from using this fountain block. And the power of this is I can actually create infinite amount of fountain code. So it doesn't matter where the reading starts and when it stops. So you don't have to wait for the loop to start over when you're reading that. And I will quickly demonstrate it. First, let's show you how fast it is. Let's go our scanner and let's read this QR code. That's it. Now I'm going to show you by skipping some of the data. So I will make this read the first one, the second one. Now I'm going to skip the third block and start from the rest. Let's scan the fourth one, fifth one, and the last one. Currently, I'm missing one block. You can see here, it has not been seen yet or decoded yet. But our next part contains data from these blocks. So if I scan it, you see it successfully managed to scan and decode all of the data inside. So now you have seen how animated QR code works. Let's deep dive and check how it is created and what is the standard the BCUR or this data stands for. First, the BCUR stands for Blockchain Commons Uniform Resources. It's a proposed standard from Blockchain Commons, and it consists of 5 stages in order to create this encoded data. The first stage is just taking anything like a JSON or any data that you have and encoded it with CBOR. What is CBOR? Well, it is kind of like a JSON, but it's in binary data format and it supports binary data by default. So it's really easier to put PSBT data into it or any typed data into it. It's actually similar to Google's protocol buffers, but it's much smaller and have a less overhead. So it's smaller than a JSON, supports binary data or your custom tags, types, dates, and has a deterministic encoding. So here I'm going to show you an example of what it is. We have our JSON data here. This is just a JSON data. And when it's converted into hex, into CBOR data, we can represent it as hex. This is the binary representation of our JSON data. But here we are not using any features of the CBOR. So here the hex block is encoded as a string. But if I encode it as an hex in the CBOR data format, you see the data is much smaller. Well, if you compare these two data, the first one, the big one, is consisting of over 1000 bytes, and the second one is over 700 bytes. So we saved 300 bytes by just encoding with CBOR. And I can show you more examples with it. So for CBOR, we can use something called diagnostic notation. It's basically just like JSON, but it supports the CBOR's own types. So let's go here, put our UR that I prepared before, and here's the diagnostic format of it. You see, this one has a Boolean data type, or a number, strings, array, object, maps, sets, regular expressions, buffer, or links. And you see 32 here, which is a CBOR type. And they are all defined in the UR Registry. So you can go here and check what the tag stands for. You can use any of these tags in a standard CBOR decoder. So let's check here again our data. 666 was just an arbitrary data that I put. If you don't put that, you can see what it decodes into JavaScript. So where we save the data mostly is the buffer here, because it can represent the bytes with bytes instead of hexadecimal text. And we have the date, regular expressions, and much more types than that. Here in our playground, we have an property inspector. You can also see its types and what it decodes into. Our next step in the encoding pipeline is the bytewords. So we have our data encoded as CBOR hexadecimal format, and you see our next step is bytewords. So I'm just going to take this hexadecimal data and show you the bytewords. Well, you see, it just looks like hexadecimal data, but it's another proposed standard by Blockchain Commons. Bytewords are human-readable representation of binary data, and it has this feature here. If I convert the bytewords in the standard format, you see that every byte represented by a word, and these words have unique starting letter and ending letter. So when I represent that in the minimal format, I can see the tuna becomes TA. The size doesn't change here, but it can be written into somewhere, and just like the mnemonics, you can write your bytes if you have a secret data or store them somewhere. The people won't understand what it is, but still you will have your own data written or saved somewhere by another representation. But for the UR standardization, we are using the minimal data format, which is just taking the hexadecimal data and encoding it in the bytewords minimal format to display. Now, our final stage is converting these bytewords into UR. Well, it's not that hard. When we have the bytewords, we click on the UR, it's just its type written first, then the bytewords representation later. So here I can say my type, and when decoding, this can be read by the reader, any decoder that supports the UR, and it immediately knows its type and what to do with it. So this could be a PSPT or your seed phrase or any of the types that has been proposed by the Blockchain Commons. And in this playground, you can see them in the registry browser that we have registered some types like HD key, and you can check their definitions from the registry browser. More formal type definitions actually reside in the Blockchain Commons GitHub repository. You can see the papers here and their definitions along with their CBOR tags. They are also registered in UR Registry of CBOR tags. So Your CBOR decoders should support them by default normally, but here it's defined by the CDDF, which stands for Concise Data Definition Language. And this is used in order to define the types of your CBOR structures. You can see here that what it consists of and what their types are. For example, it's just that our tagged keypad has these tag 4304, and the keypad means it has components inside, optional source fingerprint, which is uint33, and a depth uint8, and etc. You can read more about it in the documentation on my playground, or you can go to a CBOR website and have a look at it. So the last step is just encoding our type along with its bytewords and put it like this. Now we don't need to stop here. Now I'm going to show you how the multi-UR works. Here we have our data, and if we send it to our multi-UR generator, we have a bunch of encoder parameters. And I'm going to just keep the repeat after ratio 0.5. That means if it generates 10 blocks, it will generate 5 more blocks, which will contain the fountain code. But I will show you something in the UR definition that here you can see my uniform resource has a type called myType, and this is the first part of 6 original blocks. If I scroll down here, the magic happens after 6.6, so 7.6, which contains the fountain codes. This can go indefinitely. So if I check the QR code and pause it and go to the last block, let's check what it consists of. So 7th one contains data from the 2nd block and 4th block, and the 8th one contains data only from the 4th block. This is exactly the same as the 4th one. This is where the magic comes in. So up until now, we were just encoding and decoding arbitrary data. But now let's check something that has been already registered into Blockchain Commons Registry. It's a sign request. And here we have the UR and our data for the sign request. And here you can see the decoded version in the CBOR diagnostic format. And you can see the keys are just 1, 2, and 3. It doesn't really make sense by just looking at here what this 1 stands for. And it has a type 37. We don't know what that data is. Well, in this playground, by using the BCUR library, JavaScript library, you can decode it and check them in the property inspector. So here I can see that this is a sign request, and I can check its CDDL by clicking on it or clicking the UR Registry browser, and I can see its details. So it consists of a request ID, which is an optional, a coin ID, which is in type coin identity, a derivation path with a keypad type, a sign data, origin, and etc. So if we go to our property inspector again, I can see this is the request ID. You can see this is the coin ID. And I can actually execute functions that the library exposes to us. So here, I can say get type. And 60, if we check the CDDL, what the 60 means is actually values from slip 44 with a high bit turned off. So if we check the slip 44, 60 stands for Ethereum. So I know this is an Ethereum and has a curve 8, which is SECP 256K1. And I can do more, not just the coin ID. Let's check the derivation path, right? Here we have a bunch of components inside, and I can just call to string on it. and see its derivation path. And we can see the origin, TX type, and the addresses. Well, pipeline also allows you to run functions on the top level. So like coin ID, you can get the data here and play with it. And you can check the console to play with your types. So let's check another complex one, rather big one. This is a portfolio with the engrave proposed format to synchronize across hardware wallets. We have a bunch of data here, and if you really want to see what this is, let's go to decode that is JavaScript, and our property inspector will update it, decode it, and it can show you what this consists of. Check in the registry browser. Here, and you can see the official documentation for that in the engraves GitHub repository, what the sync protocol is and how it works. But now let's come back to the property inspector. You can see it has a bunch of coins and a metadata with the sync ID, language, firmware version, etc. And in the coins, you can check their coin identity and data inside them. And they are containing HD key, which helps us to generate the XPub and figure out what addresses that this account contains. Basically, now you can decode your URs or animated QR codes and check them in the property inspector or play with it in your developer console. You can access the values that has been decoded and you can call the library functions from here. And on the next video, I will show you how to use the BCUR library in order to use your decodings in Node.js or browser or React Native, whatever you are using, and even create your own types and communicate with the wallets that supports this protocol. So let's wrap it up. How this works. Each UR is going through a pipeline. First, if you have the UR data, it goes first to the bytewords, then the bytewords are converted into hexadecimal representation, a binary representation, and it's actually a CBOR data. That CBOR is decoded, and now we have the decoded version. And here the library is using this decoded version and creates classes for it, so you can access a more detailed representation of those in JavaScript. And if you go to the other way around, first you have your own data. It could be JSON or binary data, or if you are using the CBOR, you can put your own types in it, and then it's encoded into hexadecimal format, a binary format, that's represented by the bytewords, and bytewords are then represented by the UR. Those UR can be splitted into multiple parts, and in the end, you will have your own, here we go, you will have your own animated QR codes. See you on the next video.